this is our adventures in instructionless computation. We're going to compute at full Turing power without ever dispatching an instruction successfully. And a bit of a background on why we ever started thinking in this direction. Well, we are really interested in the computational structures which are there in the targets, but are not anticipated by their designers, programmers, and anyone who secures those systems. So looking at exploitation as a discipline, as an engineering discipline, we noticed early on that programming those structures has become the foundation of all the advanced exploitation methods. The idea that there is an underlying architecture, the extra state, the extra transitions, it was very vividly present in, say, classic Frack articles on exploitation that introduced new techniques. And so we have essentially proofs by construction that the unexpected computation is possible, and we know those as exploits. We are dealing with mathematical objects there. And so for a slogan, if I may offer one, any input is a program. The cat is resting on this red banner for the best collective that you would get if you were judged the best collective back then in the old country. Well, it's a slogan, right? So any sufficiently complex input is, to steal from Arthur Clarke, is indistinguishable from bytecode, which is executed by that which takes this input. And such input plays the role of a program. I mean, let's think about it. We don't think of packets as running on the TCP/IP stack. We don't think as heaps running on heap allocators. We don't think of inputs as running on programs. But in fact, they are, because this is what exploitation is. You deal all the time with crafted programs that cause transitions in the target, and then you ask yourself, well, what can you compute using those targets? And so we have this world in which CS started with posing the question, what is it possible to compute? Which things are actually computable? And Church and Turing constructed their awesome formalism to answer that question. And then, of course, on the other side, we have hacker researchers, exploiters, who answer exactly the same question with respect to every platform in the world as not conceived of by their developers. So it's deep mathematics that we're dealing with when we deal with exploitation as a phenomenon. And with that, the propaganda part is over. And let's talk about instruction set architectures. So we describe trustworthy operation of computers in terms of traces. We describe exploitation in terms of instruction traces. But if you think about the processor, there's all this extra state that exists in it, caching, microarchitecture, what have you. And the question is, and of course, a trapping, which is going to be our goal. And the question is, well, there is this logic. How much can we cram into this logic? How much can we make this logic do with the inputs that affect it to perform computation which does not actually touch any instruction silicon or instruction logic? And people have done that. PAX, for example, the PAX team made excellent use of iCache, Dcache, split TLB lookups to actually store policy state. And so did some others. Now, it turns out that the computational power that's in there is Turing Complete. That's amazing. So, a disclaimer. A Turing Complete really doesn't mean all that much to the attacker because you can do a whole lot of exploitation with less powerful computation systems. It's just that, to quote FX, you can't argue with root shell. You can't argue with Turing completeness. You can't, if you can build that kind of computation, there is nothing that you can't do, same as with the root shell. So essentially, that's that's why we're looking into Turing completeness. Sub-Turing architectures may be just as powerful for exploitation purposes. Wish we had a better, a more granular scale, something like the Chomsky hierarchy of computational power that gets exposed to attackers. And so with that, PFLA, which one day I read as the PageFault Liberation Army, it's actually the PageFault in linear address. Reading Intel manuals can give you interesting ideas. And well, this is James Watt. It's a toy, right? What we're going to present is really just a model. But, you know, see the swinging kettle. Maybe somebody else will build a steam engine out of that. So, people think of the x86 MMU as a lookup table, but in fact it has state and transitions. It's a whole automaton programmed by the tables, the many tables that x86 stores its runtime configuration in. And of course it can be programmed with that input data because any input is a program. So traps are kind of interesting. They are not a part of the program, but they run in the same memory space. That's interesting. A trap handler not only fires because it looked up an address in the TLB or in the page tables, and it sees the flags on it and then decides it's time to trap. It also writes. That's interesting, right? It writes the error code. Where does it write the error code? It writes the error code to the stack, to where it thinks the stack is. Now, you have data that's being read from tables, and you have data being written to where it thinks the stack is. How about we sort of close that loop? How about we write back to the data that affects the operation of the trap handler? We're sort of getting a tape of a Turing machine that way. And this is something to look for. And we looked at it, and this is what we found. Before I show the construction of that machine, I would like to say that this did not come from just the philosophy. We've been studying what I would call the trap-based design patterns. The PageFault Handler is the most overloaded element of OS policy mechanisms, reference monitors, if you like. PAX and OpenWall used it. Debuggers used it. Olibone used it to construct more complex semantic conditions on which to actually trap. Then it was used to mitigate malicious data flow, or the data flow that shouldn't be there. PAX's UDREF and the SMAP bits are a very good example there. And it's just an amazing set of hacker research publications on this, which have served as an inspiration. People went and built those machines. So, instructionless Turing machine. A bit of review. So these are the interrupt descriptor table entries. There are three kinds. You normally have the interrupt gates and the trap gates. But the 32-bit architecture also allows the task gate. And that is a holdover from previous times when you could actually trap into a new task. We're going to use that. The entry 8 is DoubleFault. The entry 14 is the PageFault. And so these are the two faults that we're going to use as a clock to our machine. Our machine is going to tick between PageFault, DoubleFault, PageFault, DoubleFault, PageFault, DoubleFault. The reading and writing is going to patch up the state, but only slightly, so that you have the next fault occurring as well. And this is how it's going to tick. This is what gets pushed by the PageFault handler, the error code, and a whole bunch of other registers if we change the ring. And so IRET instruction is the design consumer for this. But what's important is that a PageFault handler actually writes memory and decrements the stack. And what if it can't actually write what it intends to write? What if the stack is invalid, or the code segment is invalid, or the IDT entry is not there? This causes a double fault. And a double fault, of course, can also fail, in which case you have the triple fault, otherwise known as reboot. Double fault is not the end of the world. Old Windows used it for debugging quite robustly, but people really don't pay any attention to it. They think that if you've got double fault, you're screwed up already. Your OS is gone. So there is what they call the task register, which in Linux is written just once in the beginning. This is where the so-called task segments are, and task state segments are. And this is where you find, say, the kernel stack address for your system call. This is how you know where you need to choose switch your stack. And we're going to make a use of that as well. So now, if we put a task gate to be our PageFault entry, say entry 14, then the following logic takes place. And it's all in the Intel manual, right? The state, that is to say, all the registers, including our idea of virtual memory, CR3, will be saved to the location pointed by this task register. Then the new task would be looked up. There is a bit there called a busy bit. If that bit is set, then you have a double fault. You can't enter a busy task. Then you load a new state from the TSS that the register is that the IDT entry is pointing to, and then you push the error code, at which point you may also double fault if your memory is not there. And then you switch to the new task. This was the hardware task switching mechanism not used by anyone anymore, but still present. And since it reads and writes large swathes of memory, it's very convenient for us. And again, no instructions are involved. Okay, so a task gate in the IDT points to a descriptor in the global descriptor table, GDT. And the GDT points to the TSS. And TSS, it's a large structure, it's over 100 bytes, and it contains all the registers, plus the stack pointers in each ring, plus the IP, plus the CR3. We're going to use all that. And with that, controlling those structures, we're going to create instructions and data. This is the instruction that we're going to use, a single instruction, which happens to be Turing Complete, in fact. This is called the decrement branch if negative. And back then, when people were interested in minimalist machines, they found that instruction and this architecture. It's a rather expensive book, mirrored on Wikipedia. So what happens here is there is one assignment, a copy, a memory copy, and then, and this is how we will build our little glider gliding across the screen for the demo. And if that copied value is less than 4, then you branch to another such instruction. Otherwise, you subtract the 4 and go to another target. So as you can sort of see, there is a conditional jump and a non-conditional jump, and there is a bit of arithmetic, so it looks Turing complete, right? What do you need? You need arithmetic, you need loops, you need branches. So the implementation will be something like this. The key idea is keep EIP at an invalid memory location everywhere in all the task segment. So you will get a page fault every time you try to execute an instruction. Every time when you think you're done dealing with the fault handler. Now, the role of that decrement will be played by pushing the error code on the stack, and we don't actually care about the error code. We care about the stack being decremented. And depending on that, we're either going to have a double fault if the stack can't be decremented any further, or a normal continuation, which then will lead to another page fault and another iteration of our clock. And this is the long and short of it. So the page fault to double fault is the rising edge of our clock. And we save old TSS state. We don't care about that. We load the new state. That's our assignment. And then we attempt to save our fault code on the stack. And that attempts to decrement ESP. So our ESP is either less than 4 or larger than 4. And if we fail, then we leave out on the double fault. If we succeed, then the actual decrement happens. The SPSA is saved, and we go to the first instruction of the new task, which gives us what? A page fault. And so we come back. So what does the program look like? One GDT to rule them all. One TSS descriptor per instruction. So our instructions are TSSs. IDT is mapped to a different place for each instruction. This is actually a necessity because of some sanity checking that the hardware task switching does. In particular, you can't switch into the same task twice. So we keep remapping the IDT every time the world shifts from under you. And the target for branch not taken is page fault. The target for branch taken is double fault. Now, there is that busy bit that you remember, right? We need to nuke that bit. We need to make the task not busy, and this happens in the GDT. Now, we're going to be remapping memory. We're going to be remapping the higher half of the TSS, of this particular TSS, over GDT. Now, as spaghetti monsters go, this one is enormous. It's like Cthulhu sized. It's tentacles all over. Okay. And also notice the CR3, well, that's what makes it possible for us to remap it. And so let's step through this and try further heights of mind-boggling. When we actually got this to work, and Julian was amazing, I thought that we were going to go a somewhat more torturous route with page tables, but he said, hey, look, hardware task switching does it all. And that's how we build it. So EIP, if you notice, is FFFFFFFF. That will trap. There are no instructions there. There is the IDT, and it has task descriptors in the two important spaces, slot 8 and slot 14. Both tasks are available. And of course, there are the instructions, A and B, well, TSS 0 and TSS 1. Okay. So the attempt to dispatch an instruction happens. EIP is, we're trying an instruction fetch from EIP, and oops, we trap. So a PageFault handler fires, and we enter the task that it's pointing to. Before that, we're saving the current task. This is where the TR is pointing. And now we're loading the new task. And remember that variable that was copied there in the branch decrement if negative? Well, that's SP in that task. So we load that task. Now our stake pointer is loaded as a part of our instruction. And also, page tables are pointing to a new thing. And of course, there is a bit of an implementation problem, right? I hinted at it. It's the busy bit. So we need to overwrite that busy bit, okay? Luckily, CPU always saves all the state. So even if the state didn't change, so in fact, we can just overwrite that. Well, I call it the nuclear option because, I mean, to me, this trick of remapping, remember we're remapping, right? Of remapping TSS over GDT, yeah, it's, but that's how we reset that bit. And this has an interesting consequence that our TSS is actually between pages. It's at page boundary. The page boundary is right in the middle of it. And it's the values of registers that we are overwriting the GDT with. This used to be buggy. This was, as per Intel manual, supposed to produce undefined behavior. It doesn't any longer. There are people who told me that they were tripped up by this behavior, say, 10 years ago, in a TSS not contained in a single page. But our processors nowadays handle that nicely. So we decrement the ESP, and depending on whether we succeeded or not, we take one branch or the other. So we can skip through those. Now, you notice that sometimes you might actually want to return back to the same instruction that you were running, but you can't enter the same task. So we have, it seems like we have a bigger problem. In fact, it's like twice the pole, okay. So in fact, this involves a bit of math. It involves the 16 coloring scheme because we simply copy the instructions that we want to return to, bloats up the program, and of course one needs a compiler for that, which Julian also wrote. And when he brought up graph coloring, instruction graph coloring, I used to be a mathematician, and now I do this, right? You can run, but you can't hide from math. It is going to catch up with you sooner or later, no matter how far away from it you run. On the simulated frontside bus, we see just a normal a bunch of packets, which is just fine. You know, this works. So of course you need the kernel access to set this up. This machine is programmed by all the descriptor tables. So of course you're supposed to be root to do this. And of course you have to do something with 2 double faults in a row. You can't. Again, you have to graph color and copy. And all the data structures need to be aligned nicely. So it's a waste of memory. Okay. Now, having said that, we're building a machine out of what is essentially just all red pills, right? There were wonderful works with automatic finding of red pills, a fistful of red pills, and so on. Now this whole thing is one gigantic red pill that actually runs a program. Yeah. No actual emulator that we could access did this right. Initially, Julian patched books, which was the closest to the correct behavior. Eventually, he actually abandoned that patch and just worked around the only thing that books implemented incorrectly. So, of course, no one cares about emulating those features of the processor. So it goes. I mean, Linux runs, Windows runs, then you know your emulator is ready. So, what's the takeaway? When we build models of normal behavior based on instruction trace baselining, we need to also include the trap automata and the exception handling automata, because those can actually accommodate a huge amount of logic and very complicated logic at that. So microarchitectures differ in their power, differ in their extra state, and who knows, maybe this extra state will become important. So it's not all about instructions. It's not all about ISAs. And of course, any input is a program if it's complex enough. You know, here our inputs were GDT, IDT, page tables, and task structs and task struct segments. And it's weird machines all the way down. You've seen one in ELF and in ABI. Now there is one in hardware. Who knows? Maybe there are those in microarchitecture. And so thank you for listening. And I would like to thank the sponsors as well. And I would like to thank the community, the hacker community, that's hacker research community, that's been an enormous inspiration through this. It has been a rather long journey into the weird machine land. But we only, I mean, now I'm convinced that we're dealing with deep fundamental mathematics whenever we deal with exploitation. But it took all of this ingenuity and effort for all of those researchers to construct the amazing gears that just interestingly showcase the mathematical structure of the thing. And thank you for listening.
Given that it's the last talk, we probably have a lot of time for questions, even though we have to give up the room, I'm not sure. But go ahead if you have any questions. This was certainly mind-boggling, if not mind-blowing. So 2 years ago, maybe we just scratched the surface of weird machines. Clearly, this presentation now shows us that we're doing a lot more than that, and we probably have a lot more to come.
Mm-hmm. Also, if I may, we are hoping to have a either formal or informal language theoretic security birds of a feather session, depending on whether we can get the room. So please follow the announcements. We will tweet that. We will also, if you are subscribed to the LangSec mailing list, we will post it there as well, or in my and Meredith Patterson's Twitter. So hopefully tomorrow. And of course, we see those works as interconnecting because the inputs that your program processes, that your program takes, should not lead it on a journey of exploring its extra state, which is otherwise known as ponage. So there is a strong connection here with formal validation and with the problem of, with the research problem of how to construct software in such a way, practical software, that is amenable to formal validation, that doesn't take it away on the journey to ponage. Thank you.
Any questions for Sergey? Anybody?
I have a question. What are the I mean, the topic is very technical, right? And it's the first thing I ever heard of this. What are the practical consequences of that? Like,
Yes, of course. What are the practical consequences of this? A binary that uses this mechanism for obfuscation will be very interesting to debug and to reverse engineer. Having one of your processors run such a computation while giving out cues to the rest of your control flow and controlling that would be quite interesting to debug. Now, of course, obfuscation is not all that interesting, but it's something to consider. We are actually thinking of releasing several crack me's based on, or debug me's based on this. Maybe next year. The emulator faults are, of course, its own area of interest. Basically, why do we do it, right? I posit that you can't actually build a proper mechanism, protective mechanism, a proper reference monitor for hardware without understanding exactly how that automaton that is supposed to take the events and match them to your policy works. So I am sure that if one looked for bugs that come from incorrect implementation of any one of those primitives, well, interesting things might happen. But it's not an exploit per se, and it's not a vuln per se. It's it's delimiting the space in which one could look for vulns. It's like staking a claim to, if you go there, there might be something interesting there. Also, we advance by basically finding new kinds of techniques, new kinds of vulnerabilities, new kinds of computation. Now, all these things, exploits in particular, are computation. So the more we look for computation in unlikely places, the better we understand the actual systems. So somewhat of a long-winded answer, a philosophical one. But of course, if I present a machine built out of extra stuff in the processor that no one uses, that's the best I can do. Building machines out of twigs and mud, flotsam and jetsam. Oh, yes. So on GitHub, which is in the paper, the link is in the paper, there is a game of life implemented as that, as the page fault, as the bouncer between page faults. I did not bring a video, unfortunately. Well, I brought a video, but yes, it's actually also on YouTube. So my showmanship suffers. Yeah, the game of life was the demo that you will find there. Yes.
How does the game of life output the individual blocks? Just where the
Video memory. We took the shortcut and actually had instructions copying the RAM bits into the video memory. But you would do that by just basically writing directly into video memory. The venerable DOS tricks. Well, I'm an old guy.
Well, thanks a lot, Sergey. That was great.